Last time in this story, we watched a model think out loud. It wrote a problem on scratch paper, stepped through it, caught its own mistakes, and got the right answer. And that raises a question we quietly skipped. Who wrote that reasoning? Who told it to slow down, to check its work, to back up and try again? The honest answer is nobody. No engineer wrote those steps. There is no hidden instruction in there that says think carefully. What grew that whole habit was a reward, the simplest reward you can imagine, a signal that only ever said one thing. Right or wrong, 1 or 0, that is it. From a teacher that gives no hints and no partial credit, an entire style of thinking emerged. This episode is about exactly how. Not the idea of reasoning, which we already have, but the algorithm, the real one by name. Start with the reward because everything hangs on it. In the alignment episode, we trained a model on human taste. People ranked answers. A second model learned to imitate those rankings, and that learned judge handed out scores. It works for things like tone and helpfulness, but it has a weakness. The judge is itself a guess, a model of what sounds good, and a clever student learns to please the judge instead of being right. That is reward hacking. So for reasoning, researchers threw the learned judge out and used something blunt and beautiful instead. A math problem has a correct answer, so just check it. Code either passes the tests or it does not, so just run them. The reward is no longer a model of taste, it is a verifier that computes a fact. This is reinforcement learning from verifiable rewards, and the point is that there is far less left to game. You cannot flatter a unit test. You either got it right or you did not. It is not perfectly unhackable. A model can still find a hole in a weak checker, but the surface for cheating shrinks enormously. Now the machine that turns that 1 or 0 signal into a better model. The classic algorithm is called PPO, and the surprising thing about it is how crowded it is. To improve one model, PPO juggles 4 big networks at once. There is the policy, the model we are actually improving. There is a frozen reference, an untouched snapshot we compare against so the policy does not drift too far and forget how to speak. There is the reward source, whatever hands out the score. And then there is a fourth one that trips people up, the critic, also called the value network. Its only job is to look at a half-finished answer and guess, how good is this going to turn out? Why guess? Because a single right or wrong arrives only at the very end, and you need to know which earlier moves deserve the credit. That critic is a whole separate network, roughly the same size as the model you are training. So you are paying to train 2 big networks just to improve one. That cost is the thread the next idea pulls. Here is the move that made reasoning training cheap enough to spread everywhere. Its name is GRPO, and the trick is to delete the critic entirely. Remember why we had a critic, to know whether one answer is good. But good compared to what? PPO trained a whole network to answer that. GRPO answers it almost for free. Take the same problem and sample not one answer but a group, say 64 of them, all from the current model. Score every single one with the verifier. Now you have 64 numbers and look what you already have. Their average. That average becomes your baseline, the bar to clear. An answer that's scored above the group average gets pushed up, made more likely. An answer below it gets pushed down. The distance above or below the baseline divided by how spread out the group was is what we call the advantage. If you have met the term, that is just a z-score, and the group computed its own baseline from itself for free. No fourth network. The group is its own yardstick. That is the whole idea, and it is the engine behind a wave of open reasoning models. Now I have to be honest with you, because this field moves in months, not years. GRPO is the clean idea, but by 2026 it is about half a generation behind. The methods actually doing the work have names too, and they are refinements, not revolutions. The first is GSPO from the QN team. GRPO weighs the model's choices token by token, word by word, which turns out to be noisy, especially for the giant mixture of experts models, where different words get routed to different subnetworks, and the per-word signal jumps around. GSPO scores the whole sequence as one unit instead of word by word, and that single change steadied the training so much it let them throw away a clumsy workaround they had needed before. The second is DAPO from ByteDance, and it is less one idea than a kit of 4 practical fixes, with names like clip higher and dynamic sampling, each patching a specific way that long reasoning runs go wrong, like rambling on forever or wasting effort on problems the model already aces. The reported payoff is concrete. On a hard competition math benchmark, the same size of base model, DAPO reportedly scored a little higher than the earlier R10 recipe and reached it using only about half the training steps. Take the exact numbers loosely, but the shape is the point. A better recipe, not a bigger model. None of these is magic. They are the unglamorous engineering that takes the beautiful idea and makes it actually hold together at scale. Let me show you the moment that made everyone believe in this. One open model called R10 was trained the most extreme way possible. No human-written examples to copy first, no warm-up, nothing. Just the base model, the verifier, and the reward. Pure trial and error from the start. And researchers watched one number as the training ran, the average length of the model's answers. At the beginning, the answers were short. Then, with nobody instructing it to, the curve started to climb. The model was choosing to write more and more because longer answers, ones where it paused, second-guessed itself and rechecked, were the ones that scored right more often. It taught itself to think longer purely because thinking longer got rewarded. Now, one honest caveat, because this is the most romanticized result in the field. It is contested. Some base models already produce a little reflection before any of this training, so the reward is probably amplifying a seed that was already there rather than inventing it from nothing. And the polished model most people actually use, the one shipped as R1, added a small set of human examples back in at the start, just to clean up the messy output. So this purest version, R10, is the dramatic proof of concept, not the product. But the core finding stands. A bare reward applied patiently grew the habit of thinking longer. So step back and look at what we actually built. We wanted a model that reasons, but we never wrote the reasoning. Instead, we built a teacher that only knows right from wrong, a verifier, so there is almost nothing to fake. We let the model try a whole group of answers at once and use the group's own average as the bar to beat, which let us delete the expensive critic and made the whole thing cheap. We watched newer refinements scoring whole sequences for stability, a kit of fixes for scale, keep that engine running at the frontier. And we saw a model given nothing but that reward teach itself to slow down and think. Notice what is missing from that entire story. Nowhere did anyone write a single step of logic. We did not program thought. We set up an incentive and thought was what cleared the bar. Next, the natural next question. If thinking is something a model can do more or less of, can we put a dial on it and pay for exactly as much thinking as a problem deserves? That is thinking on demand.